Welcome. In this video we look at 3.4, the product and quotient rule. We continue to expand our ideas of rules that we can use to take derivatives. We will learn how to take the derivatives of a product of functions, a quotient of functions, and derivatives of functions of the form e raised to the k times x. So how about the product rule? In short, it says this. Suppose I have a product of two functions, u and v. So u is really just shorthand for some function in x, and as is v. Then the derivative of u times v is u prime v plus u v prime. Here are some examples. So suppose I want to take the derivative of x to the 4 times x to the 7. So x to the 4 is playing the role of u, x to the 7 is playing the role of v. Then the derivative is going to be the derivative of the first, 4x cubed, times the second, plus the first, times the derivative of the second. So that was my u prime v plus u v prime. How about this next example? Now, we haven't discussed the derivative of sine x. It turns out that the derivative of sine of x equals cosine of x. So with that in mind, how will we do the second derivative? Well, like before, I take the derivative of the first factor, cosine of x, times the second, plus the first factor times the derivative of the second. And that's it. That's how the product rule works. Let's take a look at a proof of the product rule. So let p of x be the product of f and g. So by the definition of the derivative, p prime of x is the limit as h goes to 0, p of x plus h minus p of x all over h. Now let's replace p with what it really means in terms of f and g. And we get f of x plus h, g of x plus h minus f of x, g of x all over h. Now this step is kind of funny. So at this point, the second and third steps have exactly the same notation. I've just made a big blank in the middle. And in that blank, I'm going to subtract and add the same thing. Here it is. I'm subtracting f of x, g of x plus h, and I'm adding f of x, g of x plus h. So I really do have an equality. So why have I done that? Okay, well here's that same expression that I just had on the previous slide. Now I can break that fraction into two fractions, and I get this fraction on the left plus the fraction on the right. Now do you notice for each fraction there are some common factors in the numerator? Let's see, on the left side it looks like g of x plus h is a common factor, so I can factor that out. And in the fraction on the right, looks like maybe f of x is a common factor. So identifying those, I can pull those factors out, and I have the limit of a product of things. Well, I have a product rule for limits, which is a little bit easier than the product rule for derivatives. It just says take the product of the limits. So I have the limit as h goes to 0, f of x plus h minus f of x all over h, times the limit as h goes to 0 of g of x, and similarly on the right. But what do you notice about some of these limit expressions? What I've put in the boxes, that's nothing more than f prime of x, that's just the definition of f prime of x, and g prime of x. And these other factors, what happens as h goes to 0? That first one just becomes g of x, since h goes to 0, and the limit as h goes to 0 of f of x, well, that's just f of x. And so look what we end up with, f prime of x, g of x, plus f of x, g prime of x, and that is very much like our u prime v plus u v prime. So there it is. There is the proof of the product rule. Let's take a look at the quotient rule. What if I have a quotient of two functions? How do I take the derivative of that? And the rule says take the derivative of the top times the bottom minus the top times the derivative of the bottom, and then divide by the bottom squared. All right, let's see some examples. So in this first example, I'll take the derivative of the top, 2x, times the bottom, so times 3 plus 8x, minus the top, x squared, times the derivative of the bottom. And the derivative of 3 plus 8x is simply 8. And then this is all times that denominator squared, 3 plus 8x squared. And I can simplify a little bit. Let's see, what do I get on top? This is really 6x plus 16x squared. And I'm subtracting 8x squared, so maybe 6x plus 8x squared all over 3 plus 8x quantity squared. There we go, that looks good. And how about a second example? Well, it's always easy to do the denominator. If you'd like, you can start with that. So the denominator is simply squared. So sine of x plus 5x squared. How about the numerator? It goes the derivative of the top, well, that's just 0, times the bottom. So there's that whole sine x plus 5x thing, minus the top times the derivative of the bottom. Okay, do you remember the derivative of sine is cosine? So cosine of x, the derivative of 5x is just 5. All right, and doing a little bit of simplifying, it looks like this turns into the fraction negative cosine x minus 5 all over sine of x plus 5x quantity squared. There we go. Now, the proof for the quotient rule is not too bad. I don't have to go through down to the definition of the derivative like I did for the product rule. In fact, I can use the product rule to prove the quotient rule. Let's go. Let q of x equal u over v, then q times v equals u. So you have multiplied both sides by v, and now I can take the derivative of both sides and use the product rule. So that'll be the first thing I do, take the derivative of both sides. So q prime v plus q v prime equals u prime. Now let's solve for q prime. Well, q prime v equals u prime minus q v prime. So q prime equals u prime minus q v prime all over v. Now let's replace the q with u over v. So the q right there. Now I can do that because remember what my q was originally, right at the very beginning of the problem. Q equals u over v. Right? So q prime is u prime minus u over v times v prime over v, and then multiply the numerator and denominator by v. So if I go v over v like that, what do I end up with? It looks like, so I'll distribute that v on top, and I get u prime v minus u v prime all over v squared. Hey, and look at that. That is exactly the rule that I was looking for. That's my quotient rule. Our third rule is the derivative of e to the kx, where k is some number. And the rule says simply that whatever that k is, bring it out in front. So, for example, the derivative of e to the 8x is 8 e to the 8x. The derivative of e to the negative x is negative e to the negative x. The derivative of e to the negative 0.2x is negative 0.2 e to the negative 0.2x. And I can do even slightly more complicated things like this. How about the derivative of e to the 8 plus 3x? Well, that sum in the exponent, I can write it as a product of exponential expressions. So this is e to the 8 times e to the 3x. And the derivative of that, well, e to the 8 is just a constant multiple, so that stays e to the 8 in front. But now the derivative of e to the 3x becomes 3 e to the 3x. And then re-express it where my exponent is a sum. And there it is. It's kind of an interesting fact. What about this? What about the derivative of e to the 8x cubed? Well, we can't do this one yet, but we will soon. In the future, we'll see rules for how to do this. So, in order to prove the rule for e to the kx, let me do a small diversion and think, how would we compute the derivative of a product of three factors, u times v times w? Well, I can think of this as u times v times w, and I'm going to take the derivative of that. So I'm thinking about it sort of as two factors, where the first factor is uv. And so that derivative, that becomes uv prime w plus uv w prime. So I've just applied the product rule to these two factors, uv and w. But now, uv prime, oh, well, that is really u prime v plus uv prime times w, plus uv w prime. And now let me distribute the w that appears on the left. So that becomes u prime vw plus uv prime w plus uv w prime. And look what I have. I have three terms. Each term has three factors. And in the first term, the first factor has its derivative taken. In the second term, the second factor has its derivative taken. And in the third term, the third factor has its derivative taken. So maybe this suggests a more general rule. What if I had four factors, four functions that are all multiplied together, and I want to take the derivative? Well, the derivative will be u prime vwz plus uv prime wz plus uvw prime z plus uvw z prime. All right, let's see how this helps us a little bit in figuring out the rule for the derivative of e to the kx. And I'll just do an example. I won't do fully e to the kx. I'll do e to the 4x. So the derivative of e to the 4x is the derivative of e to the x plus x plus x plus x, because that's what 4x is. 4x is really just 4 times x, which is x added to itself 4 times. But then all those summations in the exponent can be re-expressed as e to the x times e to the x times e to the x times e to the x. And now I can use my rule for the derivative of the product of 4 factors. So in the first term, this first factor has its derivative taken, but of course the derivative of e to the x is just e to the x. And so on in the second term, and the third term, and the fourth term. Of course, taking the derivative of e to the x just is e to the x again. Well, so this gives me 4 times e to the x, e to the x, e to the x, e to the x, which is 4 times e to the 4x. So there it is. The derivative of e to the 4x is 4 e to the 4x. So this proves this indicates the general rule for the derivative of e to the kx, where k is any number. All right, now this is a good time to pause the video and try these examples. See if you can remember the product rule and the quotient rule and the rule for e to the kx, and solve these two problems. Pause the video now, give it your best shot, and then unpause when you are ready to check your work. All right, so the answer to the first problem is that guy right there, 7 times 1 over 2 root x times e to the 4x plus 7 square root of x times 4 e to the 4x. Notice what I did. Even though it's 3 factors, the original problem is a 7 and a square root of x and an e to the 4x. It's just as easy to think of it as 2 factors, because that constant multiple of 7 doesn't make things very difficult. So that's how I figured out this problem. Now, purely optionally, I noticed that each term had a factor of 7 e to the 4x. So 7 e to the 4x, and I factored out my 7 e to the 4x, if you want to, purely optional. For the second problem, here's how I worked it out. 0, the derivative of the top, times the denominator, minus the top times the derivative of the denominator, all over the denominator squared. And this simplifies nicely. You should at least get to that step. And then, purely optional, you can do a little bit of algebra and see if that last equation is true. Alright, I will stop there. This is a nice example of the product and quotient rules. Look over these things, make sure you really understand them. We use them a lot, and I'll stop here.